So now that we have studied the discrete filters, let us discuss some common filters that we will be frequently using. One is a low pass filter, another is a difference filter, and a third one, very important, is the integrator, which is also a filter. So let us look at this common filters that you would use very frequently in day-to-day applications. So let us start with the low pass filter. So we need to build a low pass filter for discrete signals. But first, if you consider the continuous time analog domain, what is the low pass filter? A common low pass filter that we are familiar with. So if this is the input and this is the output, A by S plus A is a first order low pass filter. A by S plus A, where A is the cutoff frequency and it is related to the bandwidth and the rise time of the signal. So if this is U or U of t, is y and y of t in the continuous time domain, let us plot the input and the output. This is with respect to t. So the input, let me give a step input, and the output y takes this kind of a shape. It is, the transients are suppressed, so higher frequencies are suppressed, and you will see that it gradually reaches the steady state. If I have 1 by S plus A, I will have an error. It will go and reach the steady state value of 1 by A, right? And this rise time, or the time constant at which it rises, there is a relationship with A. So it is having some relationship here with this A frequency. So in the discrete domain, if I am supposed to have a low pass filter with input Un and output Yn, what should be the transfer function of this block? So let us look at this. So let me clear up and draw our delay block. We have a filter, right? We know how to do the FIR filter and IIR filter. I will draw the FIR filter for a first order. I am not using the canonical form. I am using the normal form where we are familiar with. So I have Un, z to the power of minus 1 unit delay, goes through A1 scaling factor, summation block, B1, the output Yn is passed through another unit delay, B1, and then you get. So you can also, this is easier, nice to visualize this representation, but when you implement, use the canonical form. Now I'm going to set A1 equals 1 minus e to the power of minus at. B1 equals e to the power of minus at, where t is the sampling time. So let me mark the values. A1 is 1 minus e to the power of minus at. B1 is e to the power of minus at. And now let us write the next state equation. Let us write the equation of y at an instant kt, yk. So yk is nothing but this value. This value is, if this is uk, this would be uk minus 1 into 1 minus e to the power of minus at will follow through. 1 minus e to the power of minus at into uk minus 1 plus e to the power of minus at into this value is nothing but, if this is yk, this will be yk minus 1 into yk minus 1. From here, getting the transfer function is very easy. Yz, the z transformed values, yz is equal to 1, same polynomial coefficients, 1 minus e to the power of minus at, uk minus 1 will become uz, z to the power of minus 1, that is the z polynomial term, plus e to the power of minus at, yz, z to the power of minus 1 delay. So you can rearrange, you can say yz by uz equals, I can take this yz term onto this side, denominator to be 1 minus e to the power of minus at into z to the power of minus 1. And what remains here, uz goes down, 1 minus e to the power of minus at, z to the power of minus 1. So simplify this, you can 1 minus e to the power of minus at divided by z minus e to the power of minus at. So this implies that this is a first order system with a single pole at z is equal to this value, e to the power of minus at, where t is the sampling time, a is the cutoff frequency corresponding to the S domain a by s plus a low pass filter. So that value. So I can say that this is the transfer function of this low pass filter, discrete transfer function, and you can use it for any of the application which demands a first order low pass effect. Then next, another important filter, the difference filter. So let me take again un, the input stream, pass it through a delay block, and I am going to tap off A0, tap off A1, pass it through an adder, and that is output yn. So this is a FIR filter. So what is a difference filter? So if I am having a waveform, so this difference filter will give you the first order differentiation with respect to time. So this is the form of the FIR filter. What we want is something like this. So let me draw a waveform like this. This is u. So let's say at some point here I'll mark it down and project it onto the x-axis or the time axis or the n-axis. This is the kth sample, kt. This is at the k minus 1th sample, k minus 1t. And the difference between these two time is t, the sampling time. This value of the input stream is uk. This value of the input stream is uk minus 1 at the k minus 1th sample time. Now what is the slope, which is the differentiation? The slope is u of k minus u of k minus 1, this is the height, divided by this time difference, which is t. Or I can say u of k by t minus u of k minus 1 by t. This forms the basis for us to decide on the scaling values. So let us, like a0 should be 1 by t, a1 should be minus 1 by t. So let us do that. So this is equal to 1 by t, a0, and a1 equal to minus 1 by t, and that will give you the differentiator difference filter. T is the sampling time, and the transfer function is as given like this, z minus 1 by tz. So you can also obtain it from, like as we did before for the low pass filter. Let us write the equation at a given instant of time kt. So y of k equals u of k into a naught, which is 1 by t. So by t, then plus minus 1 by t into u of k minus 1. So minus u of k minus 1 by t. So this is the equation for this, and z transform of that yz is equal to same coefficients 1 by t into u of z minus 1 by t u of z, and because this is uk minus 1 value before, one sample time value before, so z to the power of minus 1. So this can be easily simplified. Take out uz common, put it in the denominator, you have 1 by t into 1 minus z to the power of minus 1, which is nothing but z minus 1 by tz. So this is what this is. So this is the transfer function of a first order differentiator or a difference filter. Let us look at one more filter, which is the integrator. Integrator, again I am going to use a IIR filter, first order IIR filter. So this is the feed forward part. You are familiar now with this. Unit delay, A0, A1, summer. Output of that, I will feed back the output to a unit delay and B1. And this is the first order IIR filter. Now for the integrator, make B1 is equal to 1. A0 is equal to t, where t is the sample time. A1 is equal to 0. You may or may not use it. I will discuss much later different types of integrators, but for now let us take the simplest one where I remove this line. So I will just use this part and this part. Okay. How is this coming about? So what is an integrator? So let me go to a plot. So let us say this is the n-axis, n-domain axis, and let me have some arbitrary signal. So that is u. Now let me mark 2 points here. This is the kth, this is the kth sample, kt, and this is the k minus 1th sample. So what does an integrator do? It finds the area under the curve. So this filter is supposed to act as an accumulator. Every sample, that area under that should get added to the previous added value, and then keep on moving forward. So if I take all this, these are all this area which I have kind of shaded here is the area which is to be in the memory here. This is a memory block. So it should be in the memory and should be available here. This is yk minus 1, let us say. I'll call that one yk minus 1. Up to k minus 1, the area under the curve is available in the memory. Now to this, I have to accumulate the new area, which is now this area. So one approximation is the value at this point, uk. I take it back and find the area of this rectangle. So area of this rectangle, this distance is one sample time distance t, and the area of this rectangle is uk into t. So this uk into t I will add to yk minus 1. So that plus this will give you the new value of the area under the curve. That will be the new value at k. Then at k plus 1, again k plus 1 to k, that area of the rectangle should come in, add, and then so on. It keeps moving, accumulation. So this is the integrator action. So if I look at it, uk into t, so this is called the uk value is going back. So is the rectangular calculated by this value going back. So it's called the backward Euler algorithm. So uk, a0 is t, uk into t will come to this summer block, adds up with, this is b is 1, let us say, yk minus 1 will be the equation. So now this is 0, this I am going to make it 1. So yk is equal to yk minus 1, this is yk minus 1 into 1 plus uk into t, uk into t. So this is our equation at time instant, at one time instant, k. This is yz. This is yz into z to the power of minus 1 delayed value plus u of z into t. And from here finding the transfer function is pretty simple. So this is yz, I take it on this side, 1 minus z to the power of minus 1. This is t, which can be written as tz by z minus 1. Note that there is a pole at z is equal to 1. For all integrators, the pole will lie at z is equal to 1. That is, this is in fact the core character of an integrator filter. The 0 is at z is equal to 0, that is, or it could be at many places. In fact, the calculation of this delta area is what different algorithms comes. So you have, I could take this point uk minus 1, draw a straight line and take that rectangle. So uk minus 1, go forward, take that rectangle. That's called the forward Euler's rule. So uk minus 1 into t, that is also one possibility. Or I can make a trapezium. uk plus uk minus 1 by 2. Take that rectangle into t. That is called the trapezoidal rule or the Tustin's rule. You have the Simpson's rule, you have the Runge-Kutta rule, different. So finding the delta area, you have several algorithms. But adding it to the previous area is always there in all integrators, and that is this. This is what is giving you the pole at z is equal to 1. In the pole 0 perspective, most of us are familiar with the S-plane, the continuous time domain systems, but not so familiar with the Z-plane, which is used for the discrete time domain systems. However, till we get familiar with the Z-plane, it is good to see the graphical mapping of the S-plane and the Z-plane points. I am not going into the derivation, but I will make this statement that Z, the Z variable of the Z-plane variable and the S-plane variable are related in this fashion. You can refer to the literature books for derivations, but this is the key takeaway. Z is equal to e to the power of st. Z-plane variable and S-plane variable are linked in this way, and t is the sampling interval, the sampling period. So let us use this mapping and look at a kind of a graphical comparison of the two planes. So first the S plane, I will take the S plane. The x-axis is called the sigma axis, the real axis, and the y-axis is called the omega axis, the frequency axis. And this of course is called the S plane, which is equal to, S is equal to sigma plus j omega. So using that sigma plus j omega term here, we get z is equal to e to the power of sigma plus j omega into t, sampling time t. So this is what we will use for doing the mapping between the two planes. And for the z plane, so I have an x-axis and the y-axis. There is no specific name given to these two axes. The coordinate is polar coordinate system. So I'll call this one as the z plane. So let us take a point here. A point at S is equal to 0 plus j0. This is 0 plus j0. Now what is z? Z will be e to the power of 0, e to the power of j0 into t. So therefore this will work out to be 1. So at z is equal to 1, you will see that this point z as s is equal to 0 will map to z equal 1 comma 0. Then let me take another point. Now it is on the omega axis. So it will be 0 plus j pi by 2t. 0 plus j pi by 2t. So you will see that t will cancel e to the power of j pi by 2. So it rotates clockwise by j pi by 2. The amplitude e to the power of 0 is 1. So at 1 here, so 0 comma 1, you will see the point. So the point here maps to this. Now if I am having a series of points here between 0 and pi by 2t in the omega axis, now all have sigma 0, which means e to the power of 0 will remain, which means the radius is 1, and e to the power of j 0 to j pi by 2. So you will see a series of points here with unit radius. Now let me take another point here. Now this point this was at j pi by 2t, this will be j pi by t. So still sigma is 0, sigma 0, e to the power of 0 is 1, e to the power of j pi by t, so e to the power of j pi. So the point would be at an angle of 180 degrees here, having same radius of 1. And all the points in between here will fall on a unit circle which is drawn in this fashion. Likewise, I can have points on this unit circle, all these points which will fall here on the negative omega axis, and the negative omega axis up to this point here, which is e to the power of j minus pi by 2t, minus pi by 2t. So that will reflect as this point here. And this point here minus pi by t will be the point here. And all the points from here to here, sigma is still 0, will lie on the unit circle, So you see that this unit circle is all the points on the imaginary axis from minus pi by t to plus pi by t. So these are the points corresponding to this imaginary axis from minus pi by t to pi by t. Now let me clear. Now take this point which will map to the z is equal to 1. So you see s is equal to 0 is an integrator. Z is equal to 1 is also an integrator in the discrete domain. Now let me mark a point pi by t and another point minus pi by t. Now if I take all the points to the left of that, so pi by t maps to this point in the z plane, minus pi by t also maps to this point in the z plane. If you take all the points in the area of minus pi by t to pi by t in all the left half of the S plane between these two points, they will all have sigma as negative. Sigma negative means that e to the power of minus some value, which means values less than 1. So which means it has to be within the unit circle. So sigma less than 0 implies e to the power of sigma into e to the power of j omega, e to the power of sigma t into e to the power of j omega t. So e to the power of sigma t will, where sigma is less than 0, will result, sigma less than 0 negative, will result in values less than 1, and therefore it falls inside the unit circle. All this will map in here. Now for sigma greater than 0, all this outside, sigma greater than 0 is positive sigmas. E to the power of positive sigma t will have values greater than 1. So they all will lie outside the unit circle. So that's what all the points lying outside the unit circle are unstable. All the points lying inside the unit circle map to the left of this plane. Therefore, that is the stable region. Now let me take 3 pi by t, that is 2 pi by t more than pi by t. So another 2 pi by t. So this spans 2 pi by t. This is the base band. If you see, pi by t is a point equivalent to sampling frequency by 2. So from sampling frequency by 2 points, you will see that in the discrete domain, the base band repeats. The base band multiplies at every, you will see the base band cloning at every integral sampling frequency. So if you take all the points to the left of this plane, they also, from pi by t to 3 pi by t, again pi by t is here, the 3 pi by t again will come back to that point. So you will see that all the points to the left of that will map within the unit circle. Again here sigma less than 0. And then if I take minus 3 pi by t, all the points to the left of that will map within the unit circle. So all the points which are there within the unit circle is called the stable zone. Points outside the unit circle is called the unstable zone. This is something that you need to, is a key takeaway, significant takeaway. And you can see that every 2 pi by t, minus pi by t to pi by t is the base band, which is one unit circle. From there on, pi by t to 3 pi by t is another clone which has occurred due to sampling. That also will fall into another disk, unit circle disk. 3 pi by t to 5 pi by t fall into another disk. Like that in the other side of the omega axis also. So every 2 pi by t region will map to a unit circle disk area. And remember that all the values within the unit circle maps to the left of the S-plane, and therefore the values or the pole values within the unit circle indicate stable zone, and all pole values outside the unit circle indicate unstable zone.